Hello, ladies and gentlemen, boys and girls. We are doing motion key points. And the motion key points are going to summarize our Buggy Lab and set the stage for the next part of our unit. The Buggy Lab and the motion we're talking about for the next little bit is all going to be constant and linear. Now, in the Buggy Lab, we created graphs, and these graphs are position time graphs. So we can plot an object's position every time, and we can draw a straight best fit line there. But now I can also represent the motion here in a motion map. And a motion map tells us where the object is, and it tells us what it's doing and how long it's doing it. So if I have my little whiteboard track here, this is my whiteboard track, and it's 2 meters long-ish. So let's mark it out as 0 meters, 1 meter, and 2 meters. My buggy started at the 0 meter line, so I put one dot showing that it started at the 0 meter line, and it's moving forward, so I use an arrow to show that it's moving forward. 1 second later, it's gone about 1/2 meter, and it's still moving forward. After 2 seconds, it's reached 1 meter, and it's still moving forward. After 1, 2, 3 seconds, it's reached 1.5 meters, and it's still moving forward. And then it reaches the 2 meter mark, and it's still moving because it's crossing the finish line. This is a motion map showing the motion of the object. It tells us where it is, the when, we put down 1 dot every second, and the arrow tells us what it's doing. Now if I have an object that's going faster, then it's going to be covering more distance in the same amount of time, or it's going to be covering the same distance in less time. So here I'm covering lots of distance. I'm going up real far on my Y, but I'm not going very far on my X. So this object here is faster. On a motion map, it's covering more distance each second. So it's going farther in 1 second than the other one. Now notice what happened to my vectors there, my arrows. My arrows gotten longer because my dots every second are farther and farther apart. If I have an object going slower, then it's taking a long time for it to go a little bit of distance. So my dots on my motion map are going to be a lot closer together because it's not traveling as much distance every second, and I put a dot down every second. Now, funner yet, if I have an object that starts at the 2 meter mark and goes to the origin, then I'm going to start at a high position and go to a low position as time goes on. So this part here is going backwards. And I have it going at a medium speed. So I'm going to do a motion up for it here. It's starting at the origin and it's moving this way. And it's getting closer and closer to the origin. Now what I've been drawing on my motion map there are vectors. And a vector is a quantity that has magnitude, which means it has a value, and it has a direction. And we use the arrows to represent those vectors. So an arrow here is a vector, that's one vector. It shows us, in this case, where it is, how long, and how fast. Now, since direction can go this way or go that way, directions can go this way or this way, I have to have a way to talk about opposite directions, and in science we use positive and negative. So if I'm going to the right, I'm saying that's positive direction. And if I'm going to the left, I'm going to say that that's a negative direction. Now this makes sense if we go back up here to the graph, because the backwards one that's starting at the high position and going to the origin has a negative slope. If we calculated the rise over run, y2 minus y1 over x2 minus x1, we would have a negative slope, so negative direction. With the difference in direction, we can get more information from our graph than just how fast. If I know my speed, I know how fast. That should be how, that's an H-O-W, how fast. But if I know how fast and my direction, then I know my velocity. Velocity is how fast and that's the big part, what direction. So I can say that I'm going 5 miles per hour, that's a speed. 5 miles per hour west is a velocity. Now another difference between speed and velocity is the difference between distance traveled and displacement. Distance traveled, if I want to draw a little motion map here, distance traveled, if I go there and then I come back again, my distance traveled is the total distance. So my distance traveled, if these are each, if it's going 1 meter per second, I'm going 1, 2, 3, 4, what, 5 is meters per second, whatever, I don't know. My distance traveled is my whole trip there and back. But my displacement is where did I start and where did I finish. So displacement is only the starting position compared to the final position. So if I were calculating my speed here, I would need to know my whole distance traveled and my time. But my velocity here is actually 0 because I'm starting and stopping in the same place. So velocity tells us not only what direction, but it tells us the displacement, how far did it go from where it started to where it ended. Now we can get more information out of our graphs than we've gotten so far. If I have a graph of position versus time, this is my position, this is my time. If I have a line that starts here and goes up, and I do my motion map, this person cheated, they got a head start. They did not start at 0 meters, they started at ½ meter. So their first dot goes on ½ meter, and then they're moving forward. This person here wasn't paying attention to the start line and waited some time. So he's got several seconds where he's just standing at the start line, but then he ends up going the same speed because those slopes are parallel. So he's taking the same amount of time once he starts moving. So I can use my graph here to show distance and displacement, velocity and speed, the differences. So if I have my position and I have my time graph, if I have a straight line like this that's just showing one motion that's not changing at all, then my distance traveled, my displacement are the same, my speed, my velocity are the same. But let's plot someone doing something other than just one thing. So we've got Johnny, who's going out for a run, runs as fast as he can, then he stops to take a breather, and he walks home. But he stops to find a friend and chats for a while. So in this case, my distance traveled is going to be this line segment plus that line segment. So his distance traveled is quite large, and it takes this amount of time. So he's traveling quite a far distance in a long period of time. But his displacement, he starts here, he ends there. His displacement is only a very small amount, but it's still taking him a long time to get there. So his speed is going to look fairly fast, but his velocity, the time from where he started to where he finished, is going to look very slow. This material in this TED Ed Flip is what we will be working on for the next couple of weeks. All we're going to be doing is expanding this, doing examples of this, and practicing it. And then once we're confident with this, we'll go in and we'll throw a wrench in the works and we'll do something different. Thank you.